have 1, 2, 3, 4, 5 wonderful papers. And we're starting the day with private polynomial commitments and applications to MPC by Rishabh Badauria, Karmit Hazai, Mutu, Wenxuan, and Yupeng. And Wenxuan is giving a talk.
All right. Hello, everyone. My name is Wenxuan, and today I'll be presenting our work on this private polynomial commitment scheme and the application to MPC. And this is a joint work with Rishabh, Karmit, Muthu, and Yupeng. So first of all, just so what's a polynomial commitment? So it's a scheme that allows a prover to commit to a verifier that to commit to verify a secret polynomial, and then they later reveal a evaluation point as well as a proof to check for validity. Usually for polynomial commitment, you need to satisfy for these three following properties. First one is correctness, meaning that if the prover is honest, then that means the proof that he produced should check out. Binding means that for a different evaluation point, the prover should produce a different proof, and for different polynomial to be committed, the commitment that the prover that is going to commit is also going to be different. And also hiding means that no information can or should be extracted from the commitment. Also usually in the general setting, the polynomial commitment scheme, the polynomial is hidden to the verifier, but the evaluation point should be public. So why we're interested in polynomial commitment is because it's been quite a useful building block to construct many cryptographic protocols, such as verifiable data storage, secret sharing, as well as zero-knowledge proof argument, which is very popular nowadays in blockchain applications. Okay, so in our work, we consider a different setting where the polynomial is unknown to the prover and is encrypted. Moreover, the evaluation point may also be a secret input to the prover, which will be sent to the verifier in a committed form. So why are we trying to study this setting? And that is because in a multi-party computation, this setting is actually quite common because the polynomial as well as the evaluation points are defined based on parties' input. So we need a stronger privacy guarantee. And we call it private polynomial commitment. So in our literature, we talk about a few applications that can utilize our private polynomial commitment. One is the multi-party set intersection problem with malicious security. So this is a problem where you have a bunch of parties, each of them having a secret set, and they're trying to find the intersection without revealing anything else that's not in the intersection. And the second thing is something called the distributed oblivious polynomial evaluation, which we also use to help construct our MPSI. So for our contribution, first of all, we gave our concrete definition on this new notion called private polynomial commitment scheme, or we call it PPCOM. And for our construction, we implement a couple variant of our commitment scheme that includes a single point evaluation as well as a multi-point, or we call it batch point evaluation. And we use our commitment scheme and build a MPSI protocol with malicious security. And for our experiments, we have a benchmark result. I'm going to show some of them towards the end of my presentation. Okay, so for our constructions, right? So how do we construct our private polynomial commitment? So we use something called the inner product argument as our key building block, which you will see happening many times in our paper. So this IPC protocol is a work done by Bunes, Boodle, and Bonnet in 2018. So basically what this IPA does is it allows a prover to convince to a verifier that he knows two secret vector A and B such that their inner product is this public scalar C. Okay. So why are we using this IPA? And that is because we observed that for a univariate polynomial to perform a single evaluation is just that you take the coefficient vector as one vector, and you take the evaluation point and turn into another vector. We call it the evaluation vector. Capital T should be the one on the left. And if you perform an inner product between these two vectors, that should give you the evaluation at this point. So we can if we can somehow reduce this evaluation into an inner product, then that means we are able to construct our commitment scheme. So how does this IPA work? Well, I'm not going to discuss the detail on how it works. So if you're interested, you can look through their construction. The paper is called Bulletproof. But before we can directly use it, we need to talk about a few difference in our setting versus theirs. And one of them is that for sure, in our setting, the coefficient vector, which is the polynomial, is hidden, meaning it's encrypted and nobody, not the prover, neither the prover or the verifier knows it. Whereas in the original setting, everything is plain text. And the other thing is the details inside this IPA protocol includes operations such as combine a few commitments or performing computation on top with a commitment of a commitment and a scalar. So we need to make sure that the commitment scheme that used here should be homomorphic. So in the original literature, for the commitments, vector A, B, and as well as their output C are all Peterson's commitment. Okay. So like I mentioned, that the coefficient vector is hidden to the from the prover. So that means it's in an encryption form, right? So we don't we actually don't care where this encrypted polynomial come from, but we do care that this encryption has to be compatible with our IPA, and by that I means has also to be homomorphic. So we found this encryption scheme from a very old paper. So basically what it does is it takes a plaintext M and it's going to generate a tuple of 3 terms, such that if you want to decrypt them, you take the last term and you divide it by the product of the first 2, and also raise it to your secret key. And also keep in mind that the plaintext M is also raised by the generator G. So that means after you decrypt it, you still have to do a exhaustive search in the plaintext domain. So if you just look at the blue part, but I think the third tuple, you can see that, which is the term that has the plaintext M embedded. You can see that that's just a Peterson's commitment. So we know that that's a good sign. Okay. So now let's get back to the previous slide. So now the one of the vector C is now just a bunch of, Peterson commitment like encryption. Okay. So now you see that since one of the vector is encrypted while the other is plain text, so the inner product is no longer inner product, but instead it's a product where you raise each one of the encrypted term to the power of the public term. So it's more of a modular exponentiation. And for the inner product argument, if you want to encrypt on top, if you want to do a commitment on top of an encryption, in our paper we use this pairing-based commitment where you take you pair. For example, if you want to commit the coefficient C, you take one of the public key and you just do a bilinear pairing, and then you do a product on all of them as well as a random term on the outside. The good thing about this commitment is that you can still perform computation if you want to combine like a pairing-based commitment with a Peterson's commitment, as shown on the third line. So now we turn this inner product argument into this inner pairing product argument. So inside this IPA, so if you see a multiplication, that's basically turned to exponentiation. And if you see things like addition, that turns to multiplication. And the good news is we don't have to invent the wheel because there's already a work called inner pairing product, which is an extension of the previous work, also done by the same authors. Okay, so with that in our hand, then we should be able to reduce our private polynomial commitment schemes problem into an inner pairing product. Well, we still have a few steps to go, and one of them is this T vector well formed, because in the inner product argument, we're doing inner products, whereas in the private polynomial commitment scheme, we're doing polynomial evaluation. So there's no way to convince the verifier that, you know, this T is exactly as you describe, meaning is indeed T to the 0, T to the 1, all the way to T to the n. So the verifier, the prover needs to do some additional steps. And in our paper, we'll call it the linear test and the quadratic test. So before I go to each test, let me talk about what the prover needs to do. So the prover is going to define 3 public matrices, A, B, and C, as such fashion, such that if you multiply A to this vector T, that will give you, the first D minus 1 term of this vector T. And you do that on this vector Z, that should give you the last D minus 1 term. And if you multiply by matrix B, that should give you this vector just containing the first element, the second element T repeated D minus 1 times, such that if you multiply X times Y element-wise, that should give you the third vector Z. So we need to prove these 2 sets of constraints. So we're going to prove the first 3 using the something we call the linear test, and the last one something we call the quadratic test. Okay, so I'm just going to demo like one of them, the first one, which is X equal to A times T, because the procedure for the second and the third are the same. Since we in our experiment we implement the batch evaluation version of the protocol, I might as well just show you the full version. So recall that T is just an evaluation vector at point T. But if you want to do multiple evaluation at the same time, that will give you a 2D matrix instead, where each column of this matrix is going to be an evaluation vector for each evaluation point. Okay, so then how do we proceed? The verifier is going to produce 2 random vector for the such that this equation holds. So basically, you have A times T equal to X. We're just going to wrap this equation with S and U on the left and right. And then we're going to do some regrouping so that there's the second equation shows is that, for example, S sub A is just S times A. So we turn make sure that every term from the previous equation that is a matrix, no longer a matrix. So we only want vector. So now we reduce the first equation into a subtraction of 2 inner products. And then the prover and the verifier can do some random linear combination for the prover to compute his 2 secret vector A and B. And he's also going to send some cross term and some magic numbers to the verifier for her to compute their inner product, as well as the commitment of these 2 secret vector as well as their inner product. So now we reduce this linear test into another inner product argument. So basically, first of all, we run a polynomial commitment scheme, and then to check for linearity, we do another inner product argument. So what's left to do is to do the quadratic test. So that is X times Y element-wise equal to Z. So I think for the time being, I'm not going to show through the detail on how to do this since it's kind of tedious. But the idea is the same as the linear test, where we're trying to reduce this constraint into inner product arguments because we already have that working as a black box. I'll just give you the conclusion. Unfortunately, we couldn't reduce this into a single inner product. but instead a sum of multiple inner products. So if you want more detail, you can look, please refer to our paper. Here's some complexities for our scheme. So here M and D are representing the numbers of evaluation points and the polynomial degree respectively. Okay, so we also implement the MPSI protocol. So I'm going to quickly show you how we can use our polynomial commitment on an easier example, the 2PSI. So first of all, we have two parties. They each hold a secret set. And then one of the party, aka the verifier here, is going to interpolate on top of her set, meaning she's going to create a polynomial where the zeros are her set numbers. And then she's going to encrypt this polynomial and give it to the prover. And the prover now got his hand on the encrypted polynomial as well as a public input, evaluation point, which is his own set. Now he and she are going to engage in this private polynomial scheme. And if she says yes, then that means those evaluations, those encrypted evaluations should be correctly evaluated. If so, then she's going to do a decryption on those evaluations to check if those encryption are decrypted to 0. If they are indeed decrypted to 0, then that means that number is indeed in their intersection set. Okay. So here's our experimental result for a commitment scheme. So they're both commitment scheme. The one on the left is just single point evaluation, whereas the one on the right you have we're doing a batch evaluation. So our advantage here is that the only overhead is just gonna be the evaluation part, not the proof generating, not the verification time, since it's based on this inner product argument, which can be turned into can be public verifiable. And we also exploited on this advantage further. So this is our MPSI scheme. So for single point evaluation or like among small parties, we don't have that much of a advantage, but we can scale it up to easily 1,000 party without having too much of an overhead. So I'm just gonna do a quick summary. So that's my email, and thank you for your attention.
You do have questions?
Is there a way you can switch out the inner product argument for a different one, maybe to make the verifier more efficient?
I'm sorry, I didn't hear you.
Can you switch out the inner product argument for a different one other than bulletproofs, maybe, to make the verifier more efficient, for instance?
I suppose so, but since our construction is 80% inner product argument, so we haven't given too much thought on that.
Okay.
Thank you.
Okay, let's thank the speaker again. Okay, next speaker, paper 80. So second talk is credibility in private set membership by Sanjam Garg, Muhammad Hajibadi, Abhishek Jain, Jindon Jing, Omkan Pandey, and Sina Shehni. And I guess Shandong is giving the talk. He's not appearing in his picture. Okay, go ahead.
Thanks for the introduction. So this work is about credibility in private set membership. I'm Zheng Jing, and this work is joined with Sanjam Garg, Mohammad Hajabadi, Abhishek Jain, Omkan Pandey, and Sina Shehan. So private set membership protocol is a two-party protocol between a server and a client. Now, the server has some database with multiple entries, and there is a client with some input X. So the goal of this protocol is to have both parties to interact in multiple rounds, so that in the end, the client can learn whether his input X is equal to some database entries or not. And for privacy, on the database side, we require the input to this client X is hidden from the server. On the client side, we require the client can only learn whether his input X is contained in the database or not. And everything else about the database should be hidden from the client. So this private set membership protocol is very important and has many applications, such as exposed password checker. So in this application, the database contains some leaked password, and the client wants to know whether his password is contained in this leaked password database or not. So he can first homomorphically encrypt his password and send it to the server. And the server will homomorphically search on the database and return the answer under the encryption of this homomorphic encryption and send back it to the client. So this application has been already implemented by several companies. And the private set membership protocol also has other applications, such as private contact discovery. So in this work, we studied the following credibility issue about the private set membership protocol. So let's consider a malicious database. A malicious database can always cook up a database that contains the password under the hood of this homomorphic encryption. So he can always convince the client that the password is contained in the database. And this will cause the client to keep updating its password. So this may increase the chance that this client can choose a bad password. So in this work, we formalize the following notion of credibility. Intuitively, we request that for such a private set membership protocol, any malicious server shouldn't be able to convince the client that his password is contained in the database if the password indeed has a high entropy. And this intuition leads to our following definition of credible private set membership protocol. So such a protocol is a two-party protocol between the server and the client. And our focus is on the round optimal protocol, which is two round in this case. So in the first round, the client encodes his input X and send it to the server. And the server do some computation on the database and sends back whether there is a database entry W such that it satisfies some relation R with the input X. For example, if the relation R is the equality check between input X and this database entry W, then this application corresponds to the password checker application. So in the end, the client can decide whether to accept or reject the server's message. So if the client accepts this message, then it means that the client is convinced that there exists a database entry W that can make this relation R satisfiable. Otherwise, the client will reject. And for privacy, on the client side, we request that for any two different messages, X0 and X1, the first message for those two different inputs should be indistinguishable. On the other side, on the server side, we require the following simulation security. So we require there exists a simulator which can simulate the server's message. And the simulator only needs to take the client's message as input and also the result of the client's query. And next, we define the credibility as follows. So suppose the client's input X is sampled from some high entropy distribution D. In this case, we require the client to always reject with overwhelming probability. So more formally, credibility is defined as follows. So suppose the client's input X is sampled from some distribution D, where this distribution satisfies that for any fixed witness W, the probability that this X and W satisfies this relation R is negligible. So here, the probability is over the distribution of X sampled from some distribution D. And we require that if this is the case, then the client should reject this server's message with overwhelming probability, where X is sampled from this random distribution. So previously, do we know how to achieve this credibility for private set membership protocol? Previously, there are two approaches to achieve credibility. The first approach is to use some oblivious pseudo-random function to hash each entry of the database and obtain several hash values. And then the server will send those hash values to the client. The client knows the key of this oblivious pseudo-random function, and he can also hash his own database, his own password to some hash value. And then you can check whether there is a match between his hash value and the hash values sent by the server. So this is indeed implemented by several companies. The issue of this approach is that the server needs to send all of those hash values to the client. So the communication complexity of this protocol will grow with the size of the database. And another approach is to hash the database to a very small hash value. And then the server is going to attach a ZK snark, proving that there exists a pre-image of this hash, which is the original database, and it can lead to the correct server's message. So the issue of this approach is that the ZK snark need to use the code of this hash function. So it need to make non-black box use of the cryptographic primitive, and this could be very inefficient. So in this work, we studied the following question. So can we build credible private set membership protocol with both of the following features? So the first feature requires the communication complexity of the protocol to be sublinear in the database size. And the second feature requires the construction to make only black box use of the underlying cryptographic primitives. And here is our result. We first consider the simplest relation, which is the equality relation. In this case, we show how to build black box credible private set membership protocol in the plan model from learning with error assumption or decisional Diffie-Hellman assumption. And then we extend this equality relation to a larger class of relations, which we call them efficiently searchable relations. So here we say a relation R is efficiently searchable if there exists a branching program F with this entire database hardwired in it. And this branching program will take some input X and output the index I in the database such that this R of this X and the ith entry of the database equals 1. And more crucially, we require the length of such a branching program to be only logarithmic in the size of the database. So for those efficiently searchable relations, we show how to build black box credible private set membership protocol with trusted, transparent setup from learning with error assumption or decisional Diffie-Hellman assumption. And finally, we extend this efficiently searchable relation to broader class of relations, which is bounded depth searchable relation. And in this case, we show how to build credible private set membership protocol with trusted, transparent setup from learning with error assumption. So in this construction, our construction is almost a black box, except the bootstrapping step in the fully homomorphic encryption. So in the rest of this talk, I'm going to show you the technical details of how to build this black box credible private set membership protocol for efficiently searchable relations. So our starting point is to use the following commit and proof paradigm. So we first commit each entry of the database to some commitment, and then we build a Merkle tree on top of that. And for the client input X, we first encrypt the client's input X under some maliciously secure homomorphic encryption scheme and send it to the server. So such a maliciously homomorphic encryption scheme can be built from learning with error or Diffie-Hellman assumption for branching programs with bounded depths. And then we have the server send the hash root in clear and also attach a zero knowledge proof under the hood of this homomorphic encryption. this zero knowledge proof ensures that there exists a database entry W and its local opening with respect to the Merkle root H, such that this database entry satisfies this relation R. So this is the case when the server find a database entry that satisfies this relation. So otherwise, the server will send a message that such a database entry does not exist to the client. So the intuition behind this construction is that so this hash value can fix the database entries. And this hash value is computed outside the hood of this homomorphic encryption. So intuitively, the database entry should be independent of the client's input, and this gives us credibility. So, but to formally prove this credibility, we need to use a special hash function called somewhere statistical binding hash. So such a hash function is defined under some hash key, and the hash key has two indistinguishable modes: a normal mode, which is used in the actual construction, and a trapdoor mode, which is only used in the proof of credibility. So the trapdoor mode key is associated with some index I, and the same hash function will become statistically binding for this index I. So which means there is also an extraction algorithm, which will take some trapdoor that is associated with the trapdoor mode key and the hash value. And then the extraction algorithm will output the IO space of this input, MI. So such a somewhere statistical binding hash can be constructed from learning with error assumption or Diffie-Hellman assumption in Merkle tree style. And then to prove the credibility of this construction, we are going to first replace the hash function in our construction with this somewhere statistical binding hash. And to prove the credibility, let's consider the client with some input X sampled from some high entropy distribution D. And here is our construction. So here we use this SSB hash, and we set the binding position to a random location in the database. So we can extract a random location in the database, and let this random entry denote as W prime. Then since this W prime is extracted outside of this homomorphic encryption, so we can argue with noticeable probability, this W prime will equals to the W under the hood of this homomorphic encryption in this zero knowledge proof. And using the soundness of this zero knowledge proof, we can show if the clients can still convince, if the server can still convince the clients that this there exists a database entry W satisfies this relation R, then this W prime also satisfies this relation R. However, this is unlikely to happen because we assume this distribution D has high entropy. So in this way, we can prove credibility. But in this construction, I haven't shown you how to build this zero knowledge proof, because if you use any zero knowledge proof, we need to make a non-black box use of the hash function. So how can we build such a zero knowledge proof, avoiding non-black box use of the hash function? So our next idea is to use MPC in the head paradigm to build such a zero knowledge proof. So the idea is that we first secretly share the NP witness W to N shares from W1 to Wn. Then we run an information theoretical MPC in our head. So each party of the MPC protocol holds one share of the NP witness, and they want to jointly compute a function. The function firstly recovers the share W by XORing the input to each for all of the parties, and then computes R of X and W. So to build a zero knowledge protocol, to build a honest verifier zero knowledge protocol using this MPC in the head, the idea is that we have the prover first commit to the views of each party in this MPC protocol. And then we have the verifier send a random subset of the parties. Then in the third round, we have the prover open the commitment of the views in this subset S. So given this MPC in the head paradigm, we're going to first build a 4-round protocol, and then we are going to compress it to 2 rounds. So how do we build such a 4-round protocol? We first secretly share the database to n different shares from DB1 to DBN, and then we build a Merkle tree on top of that. Then we have the client send a homomorphic encryption of his input X. In the second round, we have the server send the hash root in the clear, and also under the hood of the homomorphic encryption, we homomorphically provide the commitment of the views for each party in the MPC protocol. Then we have the client sends back a random subset of parties. And finally, we have the proofer open the queried views of the protocol in the subset S, and also contains the local openings for the database in S. And we provided the third message on the homomorphic encryption and send them to the client. But this is a 4-round protocol, so how can we compress it to 2 rounds? So our next idea is to use a 2-round oblivious transfer. So let me first recall what is the oblivious transfer. Oblivious transfer is a 2-party protocol between a sender and a receiver. So the sender has 2 inputs, X0 and X1, and the receiver has an input bit B. So the goal of this protocol is to have the sender and the receiver interact in 2 rounds. And finally, the receiver can receive some bit XB, X subscript B. For security, we request that on the sender side, it can hide the other input X subscript or minus B. And on the receiver side, we require it to hide its input B. So then we can use this oblivious transfer to compress this 4 rounds protocol to 2 rounds. And the idea is to remove the third round message, which is the challenge sent by this client S, this random S. So we remove it and we put the random subset in the first OT message and send them in the first round. And then we also replace the 4th round message and wrap them in the second OT message. In this way, we can compress this protocol from 4 rounds to 2 rounds. So indeed, there are more details in this construction. For example, how can we homomorphically compute this commitment of the views in the MPC in the head protocol without non-black box use of the commitment scheme? So indeed, we do some pre-processing outside of the homomorphic encryption, and we homomorphically select the correct commitments. So if you are interested, you can ask questions. Thank you.
Questions? No question. I have a quick question. Did you think of proving that the password is not in the database? It doesn't seem to prove that the password is not in the database.
Yes. Yeah. So what's the question?
To prove, so if I want to check that you're proving that the password is in the database.
Yes.
Can you prove that it is not in the database?
Good question. So so if you fix the hash of the database in advance, maybe you can prove that. But so we think for a malicious server, so it's natural. So if the password has a high entropy, then it's natural for the password to not contain in the maliciously generated database. Yes.
Okay, thanks. Let's thank the speaker again. Next speaker. Okay, so next paper is paper 7. The paper is improved private set intersection for sets with small entries by Geoffroy Couteau and Dang Bui, and Dang is giving us the talk.
Yeah, thank you. So hi, I'm Dung, and today I'm gonna present about private set intersection from pseudo-random correlation generators, and this is joint work with Geoffroy Couteau. So let's start with the circuit computation. So circuit computation is an area of cryptography, and it allows you to compute the outputs of one function in circuit way. without revealing any information about the private inputs. So BSI is a specific key of MPC when you consider the function f equal to the intersection of database. And in this talk, we focus on two-party PSI. It means that you have Alice with input set X and Bob with input set Y, so they can communicate with each other. And in the end, they wish to learn the common item between their data sets without revealing any information about items that are not in the intersection set. And we consider about the security. We have two kinds of adversary, semi-honest adversaries. It means that the adversary will follow exactly the protocol and just try to learn extra information about private input of the other. And the second adversary is that malicious adversary can deviate from protocol and then make the output of protocol incorrect. BSI is one active research topic of MPC because it has many real application, for example, for contact recovery, for contact tracing, for advertising efficiency, or for Google password checkup. So now let's see about the state of the art of PSI. As I mentioned that BSI has many real applications. So this state of the art is based on the efficiency of PSI constructions. So since BSI is a specific case of MPC, so of course that all the methods used for generic MPC can be applied to the BSI. It means that you can express the function in arithmetic or Boolean circuits, and you find the secret way to compute the output of function. However, this method requires at least O and log and communication costs. So when you consider the size of data set is 1,000,000 or 1,000 items, so it's not efficient enough. And the first method to break the law about O and log n is that using the public key like Diffie-Hellman or RSA. And the BSI beyond public key usually achieve very small communication costs, but it will trade off with the high computation because of implementation of public keys. And the next method that using the Oliver transfer, and the most efficient BSI protocol based on OT using the OT extension and Oliver's key value store. So OT extension means that you have a small number of OT and you want to obtain the large instant number of OT using the symmetric key or the PIF. And Oliver's key value store is that the encoding techniques and it hides the structure of input data sets. And so recently on the top of the state of the art of PSI, there are several books, and they use a new technique called pseudo-random correlation generators, or BCG, like only or vectorly, to propose a new PSI protocol with very good efficiencies. And our contribution is also use the BCG to propose 2 new PSI protocols. So in general, there's a general framework to build the PSI construction. Like you can use the public key Oliver transfer or BCGs to build an efficient OPF. And then from this OPF, you can directly obtain the PSI constructions. So now let's see about what is the OPF and then how we can obtain the PSI from OPF. So OPF stands for Oliver pseudo-random function. And pseudo-random function is a key function, and if the key is random and keeps secrets, then you cannot distinguish between the outputs of pseudo-random function and the output of truly random function. And for BSI, we use the concept of Oliver pseudo-random function. In the ideal functionality of OPF, Alice have a private input X, and Alice will get back the PIF output on X, FKX. While Bob will receive the random key keys. And for privacy, Alice learn nothing about the key of Bob, and Bob learn nothing about the private input of Alice. So now from this ideal functionality, we can directly obtain the BSI, while Alice can input each element in her set to OPF and receive back the BRF set FKXI, while both have on the key case, so both can compute the PIF on any input. So both can compute the PIF on each element in his set, SKYI, and send to Alice. So now Alice only need to compute the two OPF set, SKXI and SKYI, and find the common items. So it means that if you can find the ways, the efficient way to construct the OPF satisfies ideal functionality, so you can directly obtain the efficient BSIs. However, like this kind of construction is hard to construct and is a less efficiency, so we can modify the ideal functionality of OPF in the relaxed ways. Now, instead of receiving only one random key case, both can receive a set of different keys, K1, K2, until Kn. And for Alice will receive the PIF set of each element in her set, but with the different keys. So Alice will receive the SK1, X1 until SKN, Xn. So now the question comes up that which message both should send to Alice so that Alice can compute the two PIF set and find the output the correct intersection set. So maybe you can think about like Alice can send the same message as previous OPF. It means that both can send SK1 Y1, FK2 Y2 until SKN Yn. But however, like if we consider these scenarios, when we have the X1 equal to Y2, it means that if the BSI protocol is correct, so Alice should recognize and then output X1 is one element belong to the intersection set. However, like Alice only have a FK1, X2, X1 and FK2, Y2, but they are different because they corresponding with the different keys, K1 and K2. So it means that Alice cannot recognize the X1 is one element belong to the intersection set. So it means that this message is incorrect. So to help both to know which element in his set will corresponding with which keys, we use the hashing techniques, and which one I will discuss in the next few minutes. So as I mentioned that our new PSI construction based on the technical BCG. So now let's see what's the BCGs. The first up in circuit computation, we rely a lot on the correlated random strings. For example, in one-time bus, before transmitting the message, Alice and Bob need to hold a pair of random keys, and the key needs to equals. So BCGs were introduced by Zubaisai to enable to compress and store the long correlated strings. And the BCG has two phases. The first one we call pre-processing phase. It means that Alice and Bob will have a very short communication code, very short communication and computation to obtain the small correlated Cs. And then the second phase called silent computation, because from this C, Alice and Bob can locally expand them to get the long string satisfy one given condition. So BCG has two features. The first one that the C can be silently expanded to the long correlated strings, and Alice and Bob only need to communicate and store a short correlated C. So there are two concrete types of BCGs. The first is we call bus only, and the second is a vector only. And only stand for obligate linear evaluation. And we are working on the subfield E and larger field F. So in the bus only, after the communication with each other, Alice and Bob will locally expand their C using the ring LPN assumption, while Alice will get the pair vector UV and Bob gets the vector data and W such that they satisfy a linear condition. Wi will equal to data I times Ui plus Vi. And when we consider the vector data belong to smaller fields, and we call it subfield bus only. So for the second type of BCG is vector only, and in vector only, Alice and Bob have a short communication to obtain the pair of seed. And then from this seed, they use the LVM assumption to expand the seeds. Alice will get the pair vector UV, and Bob, at this time, Bob only gets the value data and vector W, such that Wi is equal to data times Ui plus Vi. And we also consider when the value data belong to the subfield, and we call it subfield vector list. So the difference between the bus only and vector only is that for both, instead of receiving the whole vector data, both only receive one value data. And they use two different assumptions to obtain the randomness strings. So in our contribution, for our contribution, we use BCG to propose two new PSI protocols. And the first contribution that we have is the new PSI protocol against the semi-honest settings from the subfield vector and generalized cuckoo hashing. And our semi-honest PSI protocol can handle the cuckoo hashing having the multiple items per pin, and it has the efficient with the competitive communication cost. For example, like if you consider the set of database equal to 2 power 24, and the bit length of entries 32 bit, then the communication cost totally only 1,047 bits. And the second contribution that we propose new PSI protocol can against the malicious setting and from subfield vector and polynomial structures. And our malicious PSI protocol can secure without random oracle model or any hardness assumption. And it have a competitive communication cost even with the bad random oracle model based BSIs. So in this talk, I will focus on the semi-honest BSI protocols. So our OPF constructions. So the first Alice and Bob will involve to the subfield vector list, while Alice will get the bare vector UV, and Bob gets the value data and vector W equal to data times U plus V. So now Alice will have the secret input set X, and we present it into vector X, and Alice will send to both the vector Z equal to X minus U. So now Bob can define the set of keys equal to data times Z plus W. So if you substitute Z equal to X minus U and W equal to data U plus V, you can get the equation of key V equal to K minus data times X. So now Alice and Bob can define the PF outputs in the following ways. For Alice, for each position I with corresponding with the secret inputs Xi, Alice can define Fixi equal to the hash of IVI. And for both have the key, so of course both can compute the PF outputs on any input Y. Xiy equal to the hash of I Ki minus data times Y. So if you consider Y equal to Xi, you will obtain Fiy equal to Fixi from the equation of keys. It means that this OPI construction is correct. And our OPI construction secure against semi-honest settings, and the communication code come from only subfield vector and the code for sending the vector Z. So the code for subfield vector is sublinear. It means that the communication codes of our OPF only depend on the bit length of input set. So now let's see about the hashing techniques. In the PSI, the hashing technique will use to map n item to m bin by k hash function, and the output of k hash function is the number of bin we map the element into. And we use the cuckoo hashing for Alice and symbol hashing for both. In cuckoo hashing, each bin will contains at most one item, and one element X is put into exactly one bin SIH. And for the empty bin, we ask the dummy items. And in our work, we handle the case that it bin contain a small element instead of only one element, and we call it DK general cuckoo hashing. And for symbol hashing is very simple, but when it's combined with cuckoo hashing, it can bring the BSI in the very efficient way. So in symbol hashing, for any elements X is put into OK bin instead of only one bin like cuckoo hashing. So this is our semi-honest BSI construction. So we have Alice with input set X and Bob with input set Y. Let I recall that we already have the OPF from the subfield vector list. So now Alice will use the cuckoo hashing to map O per set to the M bins. And now Alice and Bob will involve to the OPF construction, while in the end, Alice will get the BF sets for each element with corresponding bins. And for both will for each element in his set, Bob will use the symbol hashing to map each element in his set to key bin. And now Bob have the set of keys, then Bob can compute the PF output on each element with corresponding bins. And Bob send all of the values to Alice. So now Alice can compute the two PF outputs and find the common items. So you can see that the communication cost of our semi-honest BSI construction come from the cost of OPF and the cost for sending KTM and PF values. And so finally, our theoretical comparison to the state of the art of PSI. And thank you, and I'm happy to answer any question.
Your questions? Let's thank the speaker again. Okay, we're 2-3 minutes ahead, so we can relax a bit. The next paper is paper 8.
Do you hear me? It's okay.
Yeah, I think it is. It's good to start. Yeah. So the next paper is pseudorandom correlation functions from variable density LPN revisited by Geoffroy Couteau and Clément Ducois. Clément will give the talk. Thank you.
Yeah, thank you for the introduction. So I'm going to present this work, pseudo correlation function for variable density LPN revisited. And this is a joint work with Geoffroy Couteau. So in fact, in this talk, I'm not going to talk too much about pseudo-random correlation function. I can just say that it is a very powerful primitive. It is linked with pseudo-random correlation generators that we're going to present it just earlier. But the idea here is to produce correlation on the fly in a non-bonding way, in a sense. And it has been introduced by Bob, Couteau, Gilboa, Ishai, Cole, and Scholl in this paper of 2020. And in fact, it has been made from two different primitives. The first one is weak pseudo-random function, and the second is function secret sharing. And in this work, we are in fact improving the weak pseudo-random function part. So just a reminder, a weak pseudo-random function is a function that looks random on the different inputs. But here it is called weak because the adversary doesn't have the choice of where the function is evaluated on. Please note also that here we are focusing on specific weak pseudo-random function, because in fact, in order to the construction to work, we have to, the weak pseudo-random function has to respect a certain shape to work with the function secret sharing. And this shape is somehow a matrix multiplication by a vector. So a brief outline. I will first present the WPRF we consider. Then I will go for the framework of attacks, and finally I will give our contribution. So as I said, we are focusing on matrix vector multiplication, and so I will do a little detour about pseudo-random generator to see what can be made with this. So what is a pseudo-random generator? It is a functionality that takes a short random seed and expands it into a long pseudo-random string. And a way to do a PIG is in fact to see this little seed X as the description of a long vector E with t non-zero coordinates. So this vector E is then sparse, so not random at all. But you can make its look random by multiplying it by a compressive matrix H. And this is the learning parity with noise assumption, which states exactly what we want, that given a matrix H public, the product H times E with E as monomial weight vector will look like a random vector B. We can wonder if you can have more structure for the matrix H, and in fact you can. There's different flavor for LPM with more structure, as we will see. So in fact, as I tell you, we want our WPRF, which is this function fk of x, with k the private secret key of the function, to be in fact the result of this product expansion of x times expansion of k. And why do we want that? In fact, it's because if you think about it, you want the adversary to have a large number of samples available. And in the end, the view of the adversary will be H times E again, with E being expansion of K, and each row of H being an expansion of an input, a different input. This has the thing to consider here is to note that because we want the adversary to have, let's say, n samples, then the matrix H must have n rows. And one of the conditions for our WPRF is that n should be exponentially big. Thus, there is an exponentially big amount of rows in H. And this has two consequences. First, we want the multiplication of the two vectors to be fast. And one idea in order to have this multiplication fast will be to say, okay, I will have a number of columns that is polynomial length. But the problem is that if you do this, you expose yourself to Gaussian elimination, and thus the results will not be random anymore. The second idea would be to say, okay, my matrix H has an exponential amount of columns, but if it's a matrix H that is sparse, then I can do it in an efficient way. But then a sparse matrix times sparse vector E will result in a sparse vector, and it will not be random to the random anymore. So the solution, in fact, was given again by Boletol with the idea and the introduction of variable density learning parity with noise assumption, which is in fact stating that we can use a matrix H that has exponentially decreasing density. To be a little more precise, the matrix H is in fact a concatenation of D subblocks Hi, whose length is doubling each time, and whose each row has Hamming weight W. Thus, the density is decreasing. It is divided by 2 each time. And the idea is that if you want to break the matrix H, you will have to break each blocks. But there is always one block that will resist to your attack. This is the intuition behind. So in fact, the matrix Hi has more structure in it because the Hamming weight is even regularly distributed, meaning that you can split the matrix Hi in W subblocks, such that for a subblock, the rows are unit vector. And also, please note also that the noise is in fact following the same shape as a row of H, meaning that the noise is also having an exponentially decreasing density. And it is not the noise that you are used to see in traditional papers. So now I'm going to talk about the framework of attacks. And we consider again the linear paradigm, the linear attack paradigm introduced by Boletol, which in fact consists of giving H to the adversary and letting him an unbounded time to find a vector of attack V in order to have the best bias for the distribution H times E. So here, please note also that the adversary has really unbounded time, so we can consider that he will find the best V, in fact. And what we want is that the adversary will not have too big bias with too high probability. So why do we care about linear attacks? We care about them because, in fact, a lot of classical attacks are linear, and the few that are not linear are, in fact, not the most promising against our work, and we can deal with them separately. The framework of linear attacks is also very interesting because, in fact, it's we don't have to consider precisely the details in those attacks, because as soon as it's linear, we are protected. So, for example, if one of them is improved, it doesn't matter. So going further, I'm talking about the security analysis of the previous paper again. We want to estimate the bias of this multiplication. And in fact, the intuition, as I said, is that each block will contribute to protect against some attacks. And so to be more clear, in fact, the block HI will protect against vector of attacks V of Hamming weights L being inside the interval 2 to the power I minus 1 and 2 to the power I. And because of this, every vector will have a block that hides everything. In fact, in their paper, they focus on the subblocks, HIK, EIK, and showing that if you consider just the subblocks and the bias induced by the subblock, if you can show that there is enough subblocks that have a low bias, then you can show that by applying the polynomial lemma that the block HI have good bias also. To do this, they introduce two random variables. The first one is the Hamming weight of V times the HIK matrix, and the second is ZK, which is the distance of AIK to the mean. So I'm going now to the contribution part. And so, in fact, in their paper, Bordeto proved that the VDLPN assumption was secure against linear attacks with the ideal proof I showed you just after. And the fact is the construction was not intended to be efficient. And so the security parameter is in fact very, very bad. On the other hand, we provide the first construction that has close to efficient parameter, and with a slightly different VDLPN assumption, but it is also with different analysis that we reached this result. And also we found an error in their security proof, and we proposed a non-trivial way to fix it. So I'm going not to talk about the error part. I'm going to talk about the improvements of the VDLPN assumption, and it comes in 3 different axes. So the first axis of improvement is in fact a better analysis, simply. As I said, we want to tackle the bias of the subblocks in a sense, and the bias is given by this equation. And if you apply the polynomial lemma for all the subblocks, we obtain this big product. And here we are a little bit disappointed in a sense, because in fact, what we want to prove in the end is a concentration bound on the bias. We want to prove that, as I said earlier, if the bias is too big, then it occurs with very small probability. And concentration bounds often exist for sums and not for products. So here we are a little bit disappointed. And one of the key ideas in our proofs compared to the previous one was in fact to prove that in fact you can change this product into a sum. And the intuition behind is that if a product is lower bounded by some constant, then the sum will be lower bounded by the number of elements in your product times the W roots of the bound. And by doing this, what we gain is the fact that, in fact, we are taking into account all the contribution, all the block HI and all the bias is counted. So we don't forget anyone, whereas in the previous proof, they were taking into account only the better ones, and thus forgetting some interesting additional bias. So in fact, this has a very impressive, this led to a very impressive reducing of W, which is the security parameter, because in fact we reduce the constant A we reduce the constant A in the exponential by 3 orders of magnitude, and thus W is in fact divided by 1000. The second axis of improvement was in fact to change slightly the assumption. So this is the Alpine assumption again. And in fact, the problem is that our proof is a little bit loose for the small matrices. So we load a lot for apparently nothing for the first few matrices. And so to erase this side effect, we decided to change the assumption by just replacing the first few matrices until some block HI star, to replace them by just a random block R, whose length is chosen according to the security parameter. And we set it, in fact, in order to protect against all the linear, all the attack vectors that are below a certain constant. So this led also to improve the security parameter. And the third axis of improvement was, in fact, to estimate a parameter beta. During the proof, at one moment, we want to have an estimation, an upper bound on the expectancy of the ZK parameter. And we can prove that beta, has a value that works well, but the problem is that it is still very loose again, and it's not so easy to improve it by just arithmetics. And on the other hand, it's very easy to estimate via computer simulation. And so with just computer simulation, we divided the security parameter with by 4. And so summing up, our construction is secure. It has very low bias with high probability. And we reached a W for security parameter to be 380. This is to be compared to the probative security parameter of Ball et al., which was more than 1 million. As I said, in fact, they were conjecturing that it was possible to have a W of 100, 200, something like this, but this was not backed up with concrete analysis. Remember also that this has concrete impacts on the PCF construction, and so we are the first to propose these parameters, which are in fact close to applicable. And we have also this aggressive variant that we are working on that will, if secure, if proven secure, achieve some very nice results. So this is all for me, and I thank you for your attention. Thank you.
Thank you. We have time for questions. Okay, no questions. Okay, let's thank the speaker again. So we're a bit early, but I think it's okay to go on. We'll have more time for coffee. Paper 135.
Does this work? Yeah.
Yes. So the last paper of the session is Threshold Private Set Intersection with Better Communication Complexity by Satyajit Ghosh and Mark Simkin. And Mark's giving a talk.
Okay. Okay, so yes, that's the title and we're the authors. Right, so the problem that we consider in this talk is the private set intersection, like something close to the private set intersection problem that we also saw in the previous talks. And as we have already seen before, basically we have two parties, they have a bunch of elements, and in the private set intersection problem, they would just like to determine which elements are in the set intersection and which elements are not in the set intersection without revealing their sets to each other. So at the end, they just want to know the set intersection. And in threshold PSI, we look at a small flavor of this problem, where we don't say we necessarily want to always compute the set intersection. Instead, we say, if the set intersection is large, compute the set intersection. If the set intersection is not large, then just output a bit that says that set intersection is too small. Okay, so this is what threshold PSI does. And if we have sets of size n, then the somewhat surprising, so basically if we have sets of size n, then what we mean by large enough is we say that the set intersection is larger than n minus t. Okay, so t measures how far away we are from the sets being fully equal. And the surprising thing is that with Satyajit Ghosh and me in 2019, what we showed is that contrary to set intersection, where we have lower bounds that tell us that there are inputs for which the set intersection communication complexity has to be linear in the size of the smallest set. For this problem, it's not actually true. So if you want to do threshold PSI, then the communication complexity can just depend on this factor t rather than on the input set size. So if you say, I only care about the set intersection if it's very large, then your communication complexity is potentially very small, in particular, much smaller than the input set sizes. So that's kind of like a surprising thing. And apart from being a primitive in its own right, threshold PSI can even be interesting to construct private set intersection protocols, because if I run a generic PSI protocol, as I said, the communication complexity will always be linear in the set size. But you can build protocols for PSI based on threshold PSI, where the communication complexity of the protocol will kind of like adaptively change based on the output of the computation. So if you like have a large intersection, even though you're computing PSI, your communication complexity will be very small. And this is why we study this primitive. And for the sake of this talk, actually, it won't even be too important how like we got this like communication complexity just dependent on T in the original paper, but I still want to give you like a very, very high level idea of why this kind of makes sense that you can do it. And the idea is very simple. So if I have this input set 1, 2, 1, 3, 4, 8, 9, and what I would like to compute is the intersection, then one way of like, finding out what the intersection is like some protocol telling me these are the elements in the intersection. So like to tell me this, the communication is obviously as big as the intersection size. But another way of telling me what is in the intersection is to tell me what is not in the intersection, because I already have my set. So if you tell me which elements are not in the intersection, I can take them out and I know that the rest is in the intersection. So if the intersection is very large and you have a protocol that just tells me which elements are not in the intersection, then I can compute the intersection myself locally without having to communicate a lot. So this is kind of like the extremely high level idea of how you make these protocols dependent on T, where T is in some sense a bound on like how many elements are not in the intersection, rather than making it dependent on N, which is the input set size. And in the 2019 paper, we basically had a blueprint of how to build such a protocol. And the idea was to split it into two problems. And throughout the talk, I'm talking about semi-honest security. So we kind of want to have privacy in the sense that like you only learn the output and like your input, but nothing else is revealed. But all the parties always follow the protocol honestly. Okay. And how we built the protocol in 2019 is we said, okay, we will split the threshold PSI problem into two smaller subproblems. So the first problem is we will have a cardinality test. So the cardinality test doesn't actually compute the intersection. It's just a protocol which at the end will say, yes, the intersection is large enough, or no, the intersection is too small. So this is the only bit that the protocol outputs. And then we had a second protocol, which was basically a PSI protocol, which was only secure if the intersection was actually large enough. And in this paper, we like focused on the two-party case, but the PSI protocol on the right effectively like worked in a straightforward case also for multiple parties. So kind of like if you know the intersection is large and you want to privately compute it, then this problem is, let's say, somewhat solved. And the focus of this talk is really this cardinality test. So if you want to build threshold PSI, building a communication efficient threshold, building a communication efficient cardinality test is the difficult part that kind of still needs to be solved. Okay, so what do we know about this primitive? What we know is that in our paper and then a paper by Branco et al., it was shown for the multi-party case that your communication needs to be at least linear in T. So like if you want to compute the intersection whenever it's larger than n minus T, your communication complexity needs to be at least linear in this T value. And we showed it for a two-party case and they showed it for the multi-party case. And throughout this thing, I'm kind of like ignoring the number of parties. So actually their lower bound is like number of parties times T, but I'm like sweeping this under the rug to have less variables on the slides. And in the original paper, what we showed is that if you give me fully homomorphic encryption, then actually I can build you a asymptotically optimal up to polylog factors protocol that does compute threshold PSI. And we showed that, so this is for the two-party case, and we showed that if you give me additively homomorphic encryption, so without any multiplicative homomorphism, then we can build a protocol which has a T squared communication complexity. Okay, so it's off by a factor of T from the lower bound. And then in the work by Badri Narayan, something like this, et al., they showed that in the two-party case, if you take our original protocol and you replace one step by doing it somewhat smarter, you can actually get asymptotically optimal protocol for the two-party case for computing this thing from just additively homomorphic encryption. So for the two-party case up to polylog factors, we kind of know how to do this. But then there was the question of, can we extend this to multiple parties? So we have a lot of parties, they all have size, sets of size n, and we would like to compute the intersection if it's larger than n minus t. And what basically these two papers showed, the one that I just mentioned and and the one by Branco, they basically both showed protocols that have communication complexity t squared. And the star just indicates that the top result considers a slightly weaker setting, but like we'll also ignore that. So effectively, they're still off by a factor of t in the multi-party setting. So the natural question is, can we kind of like close the gap in the multi-party setting between the upper bound and the lower bound that we have? And this is what we do to some extent. Like let's say we make some progress on this in this paper. So we gave what we do in this paper is we basically kind of like take a step back, and we're not actually building a new protocol explicitly. Instead, what we say is, if you give me a protocol that computes this threshold PSI problem in with some polynomial in T communication complexity, then our result will give you a new protocol that computes the same functionality, but the communication complexity is only T times epsilon, where epsilon is like some failure probability. So like to be a bit more precise, what we do in this work, we give this compiler in some sense. It takes as input a cardinality testing protocol that has secret shared outputs. The existing works all have not secret shared outputs, but it's very easy to modify them to have this property. So this is kind of not a restriction. And it has some polynomial in T complexity. You plug it into our compiler and you get a new cardinality testing problem. So like a protocol for the same problem. But the combination complexity is now linear in T, but has this like times epsilon factor where like basically it says that your protocol will fail to give you the correct output with probability 2 to the minus epsilon. Okay, so it's kind of getting close to T, but we're still off by like this epsilon factor. But if T is bigger than epsilon, then our protocol is better asymptotically. Okay, so I'm going to give you a high-level idea of how the protocol works in the two-party setting. And again, as I said before, in principle, it is already solved in the two-party setting, but our multi-party protocol works with the same ideas as what I will present in a two-party setting, just there will be more mess, and I'll explain why it's more messy to do it in a multi-party setting, but all the ideas are basically already here. So we have the parties Alice and Bob on the left and the right. We have this boxes which should be green, which are the elements that will be in the end intersection, and we have the boxes that are orange with this bar, which will not be in the intersection. Okay, and now the parties would like to run a protocol to figure this to solve the problem. And effectively, our protocol or our compiler can be seen as like a divide and conquer approach to solve this problem. And the idea is we will first take our sets and we will agree on some random function. And we will use this random function to split our set elements into T buckets. Okay, so here the buckets all have the same number of elements, but in principle they could have different numbers of elements. Okay, so this is an operation that they both can do locally. And the crucial observation here is that if right, so an important point for the two-party setting is that when we say the intersection is large, then the equivalent way of viewing it is to say that the symmetric set difference, the number of elements that are not in the intersection, is small. So now for kind of like this talk, you can think about it both ways. And if there are at most T elements that are not in the intersection, so if we are in the case of the intersection being large, and we split it into T buckets, then in expectation, each one of those T elements that are not in the intersection will land in one of the buckets. Okay, so like like each bucket will have an expectation one element that is not in the intersection. Okay, and this is nice because now what we can do is we basically split the problem into T smaller problems, and now we run the cardinality testing protocol on those T buckets. And even if our threshold T was big in the beginning, now we know that at least an expectation each bucket by itself will be very close to having the full being fully intersecting with the bucket of the other party in the case that the intersection is large. Okay, so if in expectation each bucket has at most one element not intersection, then almost all the elements are in the intersection. So we can run this cardinality testing protocol with like a new parameter T, where now T is extremely small. But actually what we do is we don't run the cardinality testing protocol, which tells us is the intersection large or not. This doesn't really help us to figure out whether the overall intersection is large. Instead, what we will do is we will run like a compute cardinality protocol. And the idea of this protocol is basically to say that if the intersection is large, then don't just tell me, yes, it is large, but actually tell me how large is it. And on a high level, it's very easy to build such a protocol from the testing protocol, because what you can effectively think of doing is you say, well, is the intersection larger than 5? And it says, no. Then you say, well, is the intersection larger than 4? And it says, yes. Well, you know, it's larger than 4. It's not larger than 5. So the intersection size is 5. Okay. So now if I have like some interval in which it could be, I run this cardinality testing protocol once for each possible value there. I'll get like a bit vector that will have some zeros and ones. And from that vector, I can determine the actual size of the cardinality if it is big enough. Okay. If it is, if kind of like the cardinality is not in this range, then we'll just say, well, the cardinality test says it's massive, and then we'll make the whole protocol say the whole thing is massive. Okay. So we kind of like assume for now that like in each of those sub protocols, we will actually get like a number of how many elements are in the intersection. And for example, here we have like one element intersection, one element and two elements in the intersection. The protocols have secret shared outputs. So what we can now do is we can just take those numbers, add them up, we get 4. And now we kind of like precisely determined what is the size of the intersection of like the overall input sets that we have. Okay. And again, to repeat the point that like if in one of those buckets, we would not be able to compute the cardinality because in this bucket by accident, the intersection was too small, we would just basically make our protocol by default output a large value so that if we sum it up, the whole value will be too large and we will say, well, it's bad. Right. So now we have the secret shared value. We asked, is it big enough? Again, inside of MPC. And it says big or small, and this is basically the output of the protocol that we have. So this is like the very high level idea of how you do it, this protocol. But when we go back a step, like what is the idea why this is good? To repeat it again, is that the threshold that we're checking for in each of the subproblems is very small now, rather than being the original big threshold. But here we need to be a bit careful because in the beginning I said that like, you know, in expectation, each of those buckets each of those checks will only have like one element that is not in the intersection in the case that it's large. But we obviously want a protocol that works with a good probability. So with high probability, it outputs the correct result. And what we do here is we basically do like an amplification by repetition. And what that means is that like rather than running this protocol once, we run it epsilon many times. And the idea is that like, some of those protocols will output small, saying that the intersection overall is small, or some of those will output that the intersection is big. And from that, we can actually conclude that it's big. And the observation here is that what can go wrong in this protocol? So the whole idea of the protocol is that like we have a lot of, we have some number of elements that are not in the intersection, and they will be equally distributed among the buckets. Now, the thing that can go wrong is that we throw these elements in the buckets, and by accident, a lot of the things that are not in intersection, they all land in one bucket. And from that, we conclude that overall, the intersection size is too small. So we will by accident say small, even though it's big. But the important point is that like if we say the intersection is big enough, we never make an error, which means that if we run the protocol epsilon many times and at least one instance outputs big, we know this is the correct answer. So we conclude that like the actual correct result is big. And what we just need to make sure is that like we run it often enough that at least one protocol gives us the correct result. Yes, so this is the high level idea. Now, this was for the two-party case. Why is it a little bit more ugly in the multi-party case? The main ideas are exactly the same. But one thing that is very convenient is that in a two-party case, again, you can talk about the intersection, but actually then like for the rest of the protocols, you just talk about the symmetric set difference. So you don't really care whether the sets in those buckets are of the same size or not. You just look at the symmetric set difference of those. The problem for multiple parties is that you can't do that anymore. You don't have this direct equivalence between set intersection and symmetric set difference. So you need to directly talk about a set intersection, which means that you, for example, need to ensure that in those buckets, you actually have like a fixed number of elements, because obviously you don't want to leak how many, like Bob should not learn how many balls fell into Alice's first bucket. So you need to pad them, but then if you pad them, this changes the cardinality of how many elements like are in this intersection, so it becomes a little bit more messy. But it can be done, and the underlying ideas are exactly the same as in the two-party case. Yes, questions?
Question.
So I have a question like as I know, like for the crypto waiver ZX19, like there's a Ibrin Group, like they propose some trivial attacks for these waivers, and so also the waiver also weigh on ZX19, right? So I wondering that did you consider the attack in the waiver?
No. So the Crypto 19 paper is all good. What we did is we did like in the Crypto 19 paper, we presented the two-party protocol, and then in the back we wrote a paragraph how to extend it to the multi-party protocol. But then because it's just a sketch, we didn't write one randomization factor. So basically the attack was claimed just like add one randomization factor, everything is fine. There's like the protocol works. Like there's nothing wrong with it.
Yes, thanks.
The question.
How large is the bucket? Each of the buckets?
In the multi-party, so
in the two-party setting, so there are T buckets. So how large is each bucket?
I mean, it's roughly, if the input length is n, then it's roughly n divided by t, because you have t buckets. But you don't really care how large the buckets are, because the whole point is that the protocol depends on this t value, not on the input size. So the bucket size is the input set length for the protocol, but it's irrelevant. You only care how close, how far away are, if you do the intersection between the two buckets, how far away are they from having a full intersection? And your communication complexity depends on this parameter. So in the multi-party setting, for example, you could carefully pad the buckets to like, having some probabilistic argument, but you could equally well just pad them to be n. It's like big enough, but like it doesn't affect your communication complexity, because your communication complexity doesn't depend on n anyway. It would just make your computational complexity worse, but that's not the focus of the paper.
Okay, thanks.
More questions? Okay, let's thank Mark again and all the speakers of the session. We have now half the hour and we're back in